class. Hope you guys are doing well. So this will be the last lesson. I'm not going to do any lessons tomorrow so that you guys can finish up your quiz and submit it to me on time. As I mentioned, Friday we'll have a meme review. Of course, that's contingent on people submitting memes, which I don't think they have. So right now it's looking like it might not happen, but I don't know. And let's see, we'll probably have a little get together for maybe a Zoom get together on next week or the week after, and maybe I'll give juniors some extra points if they show up or something like that. So that's kind of my plan. I am going to be helping out with the senior checkout and some of that stuff, so maybe I'll see some of you on campus one last time before the summer. But yeah, I miss you guys. It's too bad that the school year is ending like this. All right, so what are we going to talk about today? I wanted to talk about something called length contraction. Okay, and so length contraction is another effect of special relativity. And the phenomenon is this. Basically, fast-moving objects are measured to have a shorter length than objects at rest. Okay, and the formula is that the length of the moving object is equal to its length when it is at rest divided by gamma. So the faster it goes, the closer to the speed of light it goes, the more it is contracted. Okay? An important point is that the contraction only happens along the direction of motion. Okay? The contraction is only going to happen along the direction of motion. For example, let's do an example. What if there is a speed such that gamma equaled 5, for example? So what if gamma equals 5? All right. So what if I have a rectangular plate? Okay. And what if the rectangular plate is 5 meters by 3 meters? Okay. Now, what if that rectangular plate started traveling to the right in such a way that gamma equaled 5? Then what we're going to see is that the plate now looks like this, okay? And we're going to divide the length when it's at rest, which is 5 meters by 5. So it's only going to appear 1 meter wide, and this direction would be unaffected. That would still be 3 meters, okay? So that's pretty cool. If it traveled, say, downwards at the same speed, we would see it looking like this. So it would get contracted along this direction instead, and so it would now be 3/5 of a meter in that direction and 5 meters in that direction, okay? So it only gets contracted along the direction of motion. And if it was moving diagonally, it would get compressed and it wouldn't be rectangular anymore. It would be sort of a diamond-shaped, etc. So that's the basics of length contraction. So it's again, it involves calculating the relativistic gamma, which once again is 1 over the square root of 1 minus v squared over c squared. So the faster you go, the bigger gamma gets and the shorter the length of the object gets. So I want to do kind of a comprehensive example of how this works, okay? So let's suppose that a spaceship is 330 meters long, okay? It travels from Earth to a planet 22 light years away at a speed of 0.9995 c. So very close to the speed of light, 99.95% the speed of light, okay? So I'm going to ask a number of questions, okay? So the first question I'm going to ask is about how much time will the journey take? About how much time will the journey take according to people on Earth? So according to the people on Earth, they're seeing a spaceship going at basically the speed of light, okay, really, really close to the speed of light, to a planet that is 22 light years away. So how long would light take to travel 22 light years? It would take 22 years. That's the definition of a light year. A light year is the distance light travels in a year. So what that means, since the spaceship is going basically at the speed of light, we can say that it's going to take approximately 22 years. According to the people on Earth, okay? How much time? How much time will it take for those on the ship? For the people on the ship, how much time is it going to take? Well, we better calculate the relativistic gamma, okay? So, gamma, so V over C is 0.9995. So 1 over the square root of 1 minus V squared over C squared is going to be 1 over the square root of 1 minus 0.9995 squared, which is So the relativistic gamma is 31.6. Okay? Now it's going to take less time, according to the people on the spaceship, because the people on the spaceship are going very fast, so their clocks run slower. So it will take less than 22 years. So what I want to do is I want to take 22 years and I want to divide by the relativistic gamma, divide by 31.6. 22 divided by 31.6, and it's going to take 0.69 years, which is roughly 8 months. It's like 2/3 of a year, right? So the journey isn't going to take nearly as long for people on the spaceship, okay? Next question. How long does the spaceship appear? According to people on the spaceship. This is a simple question. If you're on the spaceship, then you're at rest with respect to the spaceship. So it's going to have the length that it has when it's at rest, which is 330 meters. So the answer is simply 330 meters. But what if we asked, how long does the spaceship appear to observers on Earth? And in that case, because the spaceship is moving, it would appear Lorentz contracted. And so it's going to be 330 divided by 31.6. It's going to be shorter. And it's only going to appear 10.4 meters long. So the spaceship's going to be quite a bit shorter. Last part to the question is, how far is the journey? According to people on the spaceship. So if you were on the spaceship, then your destination is, you can think about yourself as stationary and the destination is headed towards you. So actually the journey itself is length contracted. Okay? The journey itself is length contracted. So if you're on the spaceship and you're going close to the speed of light, you're not going to see it as 22 light years for the journey. It's going to be less than 22 light years. It's going to be Lorentz contracted to 22 light years over the gamma, 31.6. 22 over 31.6 is, I already did it. Yeah, it's going to be about 0.69 light years. So it's a much shorter journey. All right. So this is kind of a comprehensive example that puts it all together. So really it's just a question of, you calculate gamma and are you going to multiply by gamma or divide by gamma? Okay. So I want to stress that these are real effects that have been measured. And it's just the way the universe works. It's weird. So I hope you enjoyed learning about that, and that's my lesson for today. It's a rather short lesson, and I'll either see you on Friday for the meme review or next week for our Zoom meeting. So good luck on the quiz.